Half-Act Code. Did you see 2 messages I sent out yesterday? Or yesterday, I'm sorry, 2 days ago, after the last lecture? Did you catch the fact that there are literally 2 constants, one for electric fields and one for magnetic fields, and I swapped them in my head, which I should have caught on to whoever it was, like, were you asking about, who was it that was asking about the constant? And it's like, yeah, I don't know what its name is, but I think what you were really asking is that the right value? And if that's what you were meaning, maybe make it more obvious, because I didn't catch on to that. I wasn't really looking at the numbers in the example, but if you changed the value that I gave you, which is really one that we'll use later when we get to magnetic field, it's mu0 to the correct value for k. The math that we did ought to have worked out. And I think I told you everything else was fine. It was just I plugged in the wrong number, not 4 pi times 10 to the minus 7. That's mu0 for later. Otherwise, any thoughts on where we ended up in terms of any of the calculation questions on how it proceeds? We talked a bit about AI on, I guess, the first day, and what I didn't tell you is that Liberty has, or had a request for proposals for something called, I think it was called the AI Integration Initiative or something, which was basically their way of saying, we have no idea what to do with AI, but we know it's here, and we see it as a problem, but it ought to also be a benefit. And so they were asked for faculty submissions on things that they could do, and if they saw it as worthwhile, they would give an expanded license to use Copilot to proposals that got approved. And so I put in a proposal, and it was approved, and just last night, the license was made, whatever you call it, active. So now, I had been using all the Google tool set, and I think I'm going to do them on side by side, but the one that I was granted last night was a Copilot Pro license, which allows you to do all kinds of interesting things too. I actually used it last night already because I was looking for an email, an old one from a student that had written something, and all I could remember is vague context. And there's a new icon now in my inbox for Copilot, and I clicked on it and said, can you find an email from a student along the lines of, and then gave it one sentence, and like, oh, thank goodness, 2022. And it found it, and you imagine how long it would have taken. Couldn't remember their name, couldn't remember exactly what was said, had a vague context in mind, and AI found it for me in 3 seconds. So very useful. But the other thing it can do is, I tried it this morning, and I think it didn't quite do the right thing, but it integrates all of the Office suite programs together. So in principle, I should be able to receive a data set, let's say in my inbox, and from the inbox say, hey, can you make a spreadsheet out of this and visualize the data and tell me if there are any details that are worth noting there? And it ought to automatically extract it, open Excel, and do that for me. And how well it does that is left to be seen, because like I said, I just got the license last night. But I'm going to be trying to do things with AI, and mainly as an experiment, just to see how it works. Because, again, from my side, the long-term picture can look pretty weird, like we discussed. But in the short term, it ought to be a tool to make what we do here more effective, both on your end and on my end. So, like I said, I think it's dumb to say don't use AI, because first of all, you're probably going to do it anyway. And why wouldn't you? If go back a generation or two, and it's like, don't use a calculator. Like, why? Because if I could get the number crunching done real fast, I can spend time on other more useful things. Think about the things that you do with a spreadsheet today. That would be just unbelievably burdensome in terms of the time, just to work out by hand, and then you hope you don't get a digit wrong someplace along the way and mess up your data. So we don't even think about doing those sorts of things anymore. And so somehow AI is supposed to play a role like that, at least in the short term, to be a personal assistant to make you more efficient at what you do. But of course, that immediately requires some adaptation of the curriculum say like, well, now if this is a trivial thing for him to do, what am I going to actually expect that he do as a student or she do as a student? And those are questions left to be answered, I think. The bigger concern, I really think, is that existential crisis looming over all of us. It's like, well, will AI do everything for me at one point where I have to redefine my existence and my purpose? Who knows? But in any case, one thing that I set up with my modern physics class just yesterday, was I was interested in seeing how well it could, and this was Gemini through their, there's this thing that's called AI Lab, where you can customize the AI to do what you want it to. And what I did was said, hey, your name is Albert, and I was thinking of Einstein, and I was like, you're a TA for the modern physics course for junior level undergrads. Here's a link to the course text. Here's the syllabus, and help students, but don't just give away answers. And then I tried it, turned it on, was like, hey, so I'm wondering about what the difference is between scattering and absorption. And I was waiting for it to not know, and gave me a fantastic answer. And then I tested it. And, I think the best test after, I was doing a bunch of things, but at one point I was like, wait a minute, I wrote a section of this text that I know is, you can't find it written the way that I did it. The math was, you'd have to dig deep into 1920s journals to find something even similar. And so like, if it's actually learning from the document I linked, and not just having been trained off of everything on the internet, it ought to be able to answer these questions. Let's see what happens. And I started asking questions about those sections, and it was amazing. And I kind of went away going like, what good am I? But the purpose was, have this thing act like a TA. So I told my class, like, look, I don't want to not see you, but I do need to do something with this proposal that I got approved for, and make use of AI and figure out what it can do to, really, if I think about my job, it's not that during office hours I don't want to see you guys, but there are a lot of questions that could be easily answered by AI where you don't need to walk across campus to see me. And I could be doing cool things like learning about AI, I guess. Now my job's going to be obsolete soon if I wasn't distracted by a question. And so what I set up was an AI TA. And I asked them not just to use it, but there's a Google form that says, well, if you do use it, and here's some questions like, how did it go? What did it disappoint you with? What did it surprise you with its capabilities? How much time did you interact, and things like that. So like 4 questions, 5 questions every time they use it. And I'm going to try to set something up like that for us. I realized, at least on the Google side, when I tried to do something similar, the book, the PDF that we have was too long for its limitations, but possibly with the Coulomb license on the professional side, it'll take millions and millions of characters and be able to do that. So again, office hours, if you really need to see me and AI can't help you, feel free. But otherwise, I'm going to try to do that and set that up, and you guys can see how weird it is to interact with. I don't know, the best way to think about AI is sort of the composite of human knowledge in one place. It's like a giant meeting of a lot of people in the world all in one place that don't talk over each other and somehow respond to you as a singular entity. Or maybe it's a new organism, I don't know. It's weird. All right, so why don't we pray and then head in the direction of where we left off. Lord, thank you that your mercies are new every morning, that every day is an opportunity to die to ourselves and to live for your purposes, and really to be faithful in the things that you've put before us on a day-to-day basis. And I do pray that we would seek first your will for our lives and the things that you want us to do and the directions you want us to go, in the big ways and the little ways, like moving across the country or doing our homework or learning about AI or whatever it is that you have on our plates at this time. We pray that you prepare us for a future to continue to be useful to you as witnesses for Christ. Help us see your glory in the works of your hands, even in the abstract realm of physics and the mathematics that runs the universe that you made. And, thank you for this time in Christ's name. Amen. All right, so we left off on that force problem that I used the wrong constant in, and I think we'll springboard from there to us and take a slightly different angle. I mentioned to you that 3-body dynamical systems have never been solved by hand. And that means any 3 interacting things like gravitationally Earth, Moon, Sun, we're lucky that it's as stable as it is, because we can't actually, Newton couldn't, and we still can't work out that mathematics by hand. But that also means things like if you wanted to visualize those, remember last time we had this picture of 3 charges sitting at, was it like this? Making up what happened to just be a 45, 45, 90 right triangle. That if these 3 charges, whatever their signs were released, there's no way that they're going to stay still and be in equilibrium. And so, a question that might arise is like, well, obviously this won't, but is there some different configuration that would? And if the answer is yes, or if the answer is no, it's interesting, but then you could ask a further question, that is, well, for what numbers of particles is it possible to make stable configurations versus not? And so I thought as an exercise, we could start with sort of asking that question, like, is it possible to, starting with a value of n equals 1, and then 2, and then 3, and then, keep on going, is it possible? And if so, what does that configuration look like, and so forth? And I'll do the first one for you. That one's easy. There it is, and it's yes, meaning it's by itself in the universe. Nothing's pushing or pulling on it, so it's happy, it's in equilibrium, no net force on it. I did my job today. What about 2, though? So what about, and of course, and what you're free to do, cheating is putting it at infinite distance. So as long as you consider the separation distance finite, you're free to flip signs however you want. Relative magnitudes can change, but the idea is 2 charges. Could you find 2 of them such that you place them in the right orientation, the right signs, the right charge magnitudes, such that you just let them go and they're happy to stay there? What do you think? Can that work with 2? And if you're shaking your head no, why do you not think so?
If you've got opposite signs to be right.
So I mean, an easy thing is, and will it matter what the relative magnitudes are?
No, as long as you're
Yeah, you do this, the forces are pulling them inward, and they come together, and that's obviously not stable. And you have to, if you wait for them to somehow join up, then you're asking different questions, like what happens with them when they collide, and what are they, and what's their radius? That's not really the same question. And of course, if they had equal signs, they also aren't happy to stay there, because then they just zoom away, and that's not equilibrium either. And all right, so 2 is a fail. So this one works, this one doesn't work. What about a 3rd? So what's, first of all, the geometry that you're thinking of when you're thinking of 3? You want straight line? Okay, because obviously, probably when you hear n equals 3, you have 2 ideas that could come to mind. You could, an equilateral triangle might come to mind like this, right? And then you were saying linear, so what were you thinking in terms of linears? Subdivide, like this? Okay, so you got those 2 options. Can either one of them work? Yeah.
Would it work if you had a positive or negative in the middle, and then 2 opposite sides of a linear path?
So you're looking at this one.
Yes.
Yeah, so something like sides are equal, center is different, and obviously, quite possibly. Will this ever work, by the way? No, you can imagine that this is just going to be bad in every which way. Either all fly apart, or one of them pulls in while the 2 fly away, and that can't work. But this one actually does work, but you have to, that's a check mark, you have to get everything just right. Obviously it has to be symmetric in the sense that whatever you call that, it's the same as, this. And it certainly won't work where these guys have equal magnitude and only a switched sign. And that's easy to show without doing any math if you consider, like, well, okay, because of symmetry, and by the way, symmetry is a good place to, a good topic just to have a brief discussion about. There are lots and lots and lots of problems that if you don't somehow find a way to exploit symmetry, your job will either be way harder or impossible. And we'll see examples of that as we go by the course. But this one, if you've already made it geometrically symmetric, meaning symmetric around the center line situation, then really your test for can this configuration work, really boils down to only this guy, or that one, one of the ends. If you can convince yourself that this one feels no force, then the whole thing is stable. And you don't really ever have to look at the center one because of the symmetric situation. Whatever the right one's doing to it, the left one's doing the opposite because of that mirror symmetry. And so, I mean, is it clear that, let's say they're all positive, first of all. This one in the middle is going to be pushed rightward by this one because it's repelling the left side, so the center one gets pushed to the right, but it would also be pushed by this one and back to the left. And so the center one's happy regardless, so long as these charges are equal, and without that symmetry, didn't have any hope of staying together in the first place. So are you guys, does it make sense that you don't even have to test whether the center charge stays there or not? So your whole burden is one of the sides, we'll take this one, and you can see right away that if big Q and little q happen to have the same exact magnitude, is there any hope of this one staying still? And why not?
Because the distances are different.
Yeah, of course. So, if you're thinking about, Coulomb's law as a, so here's a case where it might be fine to think about it as a magnitude, right? So we have K that I got wrong last time times the product of the charges over distance. So if we're thinking about this one, the first term looks like that, and R would be A. The second term has two Q's in it, so the other one is FQQ over, and if I plug this in, I don't know, put A squared and 2A, quantity squared, right? Those two are somehow going to have to be the same thing. And how could it be if these guys were the same value, if big Q and little q are the same value? Do you see what's going on here? This is the push to the right from that guy, how strong it's pushing rightward. So it's the, I'm sorry, what did I just do? K, well, that's good start. So K, the force is, so this is the rightward force, K times the product of the charges over the distance of separation, which is 2A squared. And here's the pull, hopefully, which means we're going to have to flip signs, leftward, which is K times the product of these two charges times their separation squared. So what we obviously need for it to work out is for those two terms to be equal in magnitude, right? Does that look sensible to you guys? Yeah? No? Thumbs up? You want?
Is the difference in the application of those two equations there?
Say it again?
What is the difference between those two equations? Like, which one do you use where?
No, so this is, so generic version is the magnitude of a Coulomb force is always K times, I'll write it as Q1 times Q2 over, if you want just magnitude, we don't have to think of anything besides separation distance and the charges. Of course, we had written it, with this way when we had actual coordinates and want to work it out. And maybe what we can do is both ways today, even for this problem. But this is the same thing, just in disguise, and in a much more powerful way where you can deal with, configurations like we had last time very easily without having to do any trig. But it's nice to see both sides. But this is that equation, except the magnitude of this. And if you remember simplifying this guy, what you get if do you remember doing that? I don't, so if you do that, this turns into an inverse square law. And the top, when you hadn't taken the magnitude, just has a unit vector then. But if we get rid of that, the magnitude of the unit vector is 1. And the whole equation boils down to this. The force between two charges, the magnitude of the force. So we're just looking at the scalar, like how hard is it being pushed or pulled. And so the idea is, well, if I want to know how hard this one is pushed by this guy, well, it's K times this charge Q times that charge Q over how far apart they are, which is obviously 2A. And then that quantity has to be squared.
And then the one above that
That's-
is just the middle intersection.
That's between these two. Yeah, so how hard this one gets pushed by that, or pulled really, it's going to have to be a pull. Instinct tells us a pull, and that just means that that sign is going to be opposite.
Okay.
So does that make sense to everybody? So see how that math, what the ratio of big Q to little q is, or vice versa, whichever way you want to find it, needs to be in order for the push and the pull to be equal. It does. So, yeah, you end up getting that little q equals 4 times big Q, and opposite inside. Now, what's interesting is the Why the opposite in sign?
Just one is positive and the other's
Yeah, if it wasn't, like say they're all positives, and this one gets pushed to the right by both of them, and there's no chance of that system remaining stable. So what has to happen is, obviously Q and Q, they're the same charge, so they're going to be the same sign regardless. So there's definitely a push to the right from that guy. Well, the only way to balance this then is it has to be pulled to the left by the center one, and the only way it's going to be pulled to the left by the center one is if these two charges have opposite signs, right? Is that sometimes just give me a thumbs up or something so I don't get the blank stare and wonder if it's making sense. Why don't we try, just as a math exercise, if nothing else, to take this and use it for this problem, just as a quick exercise. And what, so in order to define position vectors for the three charges, what do we first need to define? In order to say the position of something is, an origin, right? So where would it be? I mean, you have a choice of where you put that origin. It would be pretty, let's say, not clever to put it down here or up here. To put it anywhere other than along the axis that you have would be kind of silly, because then you're putting y components that don't need to be there on all those on both of those, or really all three vectors. But then you have a choice, like, well, I could put it here, I could put it there, I could put it there, I could put it some random place along the x-axis, which would also be a kind of strange choice. So it really doesn't matter. I mean, the math will work out regardless. But where do you want to put it? At the big Q in the middle. That's funny, that wasn't my choice, but that's okay. We'll do it that way. So we'll put the origin right here. So there's the origin of our coordinate system. And why don't we label them? I'll call this charge 1, charge 2, charge 3. So if I do that, position vector R1, what does it look like? Yeah, A I hat plus 0 j hat, all right. R2. Yeah, I'll just put 0 vector. Oh, maybe I'll write it as components. And R3, is this too low? I think it's still okay. R3, what's that going to be? Yeah, I think I heard negative AI hat plus 0 j hat. All right, so then if we go back and use this, so what we're interested in is the force, the net force on charge 1 on this guy. So force on 1 is going to be force on 1 due to 2 plus force on 1 due to 3. And these two terms, we get K, Q1, which is the little q, times Q2, which is the big Q, times R1 minus R2. So what do we get? R1 minus R2. What's that going to give me? Yeah, just AI hat plus 0 j hat. So this is already the difference, right? So this, you guys following that? So when you take that vector A0 minus 0, 0, you just get the same thing as R1 over magnitude of, same thing, AI plus 0 j cubed. What's the magnitude of that vector? Like, how long is it? It's A, right? So this literally turns into K, Q, AI hat. I'm going to leave off the 0 over A cubed. All right, so that's the force on 1 by 2. And of course, if we wanted to, we could immediately do that. And the second term is K. What am I plugging in now for the Q's? I got coffee here, so I can wait. Both little Q's, right? I'll write them out first, and obviously I could just square it, but and then what's the numerator on the vector difference going to look like? It is. So AI minus a negative AI is 2A, and then of course 0, over, same thing, magnitude of this vector. Usually, I mean, almost always, the magnitude, we have to take the square root of the sum of the squares, but since one of them is a 0, you can just immediately extract the only component as the magnitude. Right? Does that make sense? So this is obviously, I don't have to do the magnitude. I can just do 2A and know that that's cubed. and so here we have, that's F12. I guess I'll just write this, KQ squared times one of the, this obviously turns into 8A cubed. Cancel one of those and I have a 2 on the top. So this gives me my 4A squared I hat. Right? You guys see how that turned out? So this term is 8A cubed. I cancel an A. I cancel 2 over 8 to make 1 over 4. And that's the end result for this guy. So this is the force on 1 by 3. And what do I need? How do I deal with these? What do I want that force to be? I want it to be 0. So I want to be able to add these two together and get 0. So my goal is to take F12 plus F13 and to get a 0 vector out of that. So that is K little q, big Q in the I hat direction over A squared plus K Q squared over 4A squared I hat equals 0, which obviously means pull one to the other side and flip its sign. And flip its sign. Divide out a K, divide out the little q, divide out an A squared, and I have the answer. So Q equals negative, look at that, Q over 4. No, 4Q. Did I do that? Yeah, oops, negative 4Q. So do you see how that, the interesting thing that comes of it is automatically it suggests to you, oh, yeah, look, the signs have to be opposite of those charges, or else it's not going to work. And but the same thing that we pulled off the other way. Good exercise just to see how that equation works out and doesn't do anything different. And really allows you to sort of mindlessly just crunch through the math rather than having to be like, oh, wait, the signs have to also be different. Does that make sense? All right, so we got this one taken care of. What about 4? What are the thoughts there? In fact, I'll say it is possible. Why don't you guys talk to people next to you to see if you can figure out what the configuration looks like? And maybe try to do the math. Use symmetry. It'll be your friend. And see if you can get an answer for that n equals 4 case. Yeah.
Just kind of a question.
First of all, that's a 2a cubed in the denominator.
Yes, it
right?
is, yeah.
That's a 2a cubed.
Yeah.
What's your reasoning behind going from those coordinates that are 1, 2, 3
Mhm.
up to that equation?
So,
It's like f1
yes.
on 1 by 2.
Yeah, so that's that numerator, this term is coordinate 1 minus coordinate 2. So that vector minus this 0 vector is the numerator of the first term. And then 1 minus 3 is this term. And whatever you have in the numerator, that vector's magnitude is what belongs to the denominator. So this 2a thing, it's the 2a, the magnitude of that vector also in the denominator. So
Solves the force just of 1.
yeah, that the effect of each of those equations, the 1, 2 solves for the force that charge 1 feels due to charge 2.
Okay.
The second equation is what it feels due to always in pairs. Yeah, and if there are 54 other charges that are pushing on that, then there's 54 terms in the sum, which obviously suggests that maybe I want to do something differently. Either have a computer do the math, or is there a way to turn this into an integral? And of course, you can't turn something like this into an integral because it isn't a continuous distribution, but we're going to get to that next. But sometimes you do find continuous distributions, or ones that at least in the macroscopic realm look like it.
Okay.
Yeah.
They can make this basic. Then you just solved it out.
Yeah.
Simplify it.
Yeah. It's just algebra after
The
that.
negative, you asked the question, like, what would Q be then?
Mhm. So the only thing that matters is the ratio of them. It really doesn't matter whether it's a huge charge and 4 times as huge a charge, or tiny and 4 times as tiny, or well, 4 times less tiny. So it's the only thing, in order. So 2 things we notice that don't matter. It doesn't really matter what A is, so how far apart these things are. As long as it's symmetric about the center, it doesn't play out in the math. And the absolute magnitudes don't matter either. It's just at the end, guys have to be 4 times as large, and opposite sign is the one in the center. But it would work with, as long as the ratio is right, it's stable.
And how did we know it was negative 4?
I mean, on the right side, the math gave you that. Because there was that 2 over 8 that just fell right out of the math. You didn't even have to think about it. But the conceptual why does it need to be, well, if you think about a force that drops off with distance squared, from the endpoint perspective, you look at what the center charge is doing, and it's a distance a away from you. The one that's twice as far away automatically is going to have 4 times less influence. And so you need that to be compensated for.
3 times as far as can be 9 times less influence?
Yeah.
Okay, and that's what we talked about the other day a little bit.
Yeah.
That's a fundamental rule of distance and relation between the force.
Yeah.
Right?
Yeah.
So it's always going to be, if there's 2 times distance, it's going to be 4 times less.
Yeah, less influence. Yeah.
Okay. And we said 2 times the distance. That was between which points?
Always from the vantage point of the one that we're worried about, what is it feeling? So from this guy's vantage point, that one's twice as far away as this one is. So in order to compensate for the doubling of distance, it has to have 4 times the charge.
Times. And then how do we know that the big Q goes in that equation? Just because that's the other.
Yeah, I mean, there's only 2 things influencing this guy. And the weird thing, I mean, it's not a bad question to ask that, but the way at least that we've figured out, and it seems to be right, how natural laws at every scale operate, is we only ever have to worry about pairs of things interacting. And even in like a body or a molecule, and how does matter hold together, you might think about this almost continuous stuff, but if you pause and be like, that continuous thing is just this thing being affected by everything in its surroundings, so all these pairs plus all these pairs of these other things plus all these pairs, and it becomes a big problem, but that really is the way fundamental forces work. They're paired force laws.
Okay.
So what kind of geometry did you guys come up with? Okay, so I heard square. Obviously 4 suggests square, but does it work? So what were you going to do on the corners of the square? Yeah, okay, so if you yeah, if you did this, it might look promising at first. It doesn't actually work, though. You could satisfy two, but not the other two, is the way that it works. And at first, you might be like, well, why not? And it's a distance issue. It turns out that square might be an answer for a higher value of n. But somebody said triangle. What kind of configuration were you thinking if you're thinking triangle? Yeah? Yeah, so probably the picture I started with n equals 3, except something to hold it all together. So obviously equidistant in the center. So something like Q, 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 which obviously without that, I mean, how would they move if they were, just imagine I could do this. Carefully place on an equal outer triangle 3 exactly equal charges, same sign, and then stand back. What's it going to do? How do they move? Yeah.
Probably pull in until it reaches some.
Well, wait, they're all plus, 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 let's say. So are they pulling or pushing?
Expand.
Yeah, and symmetry. Again, this I don't know if the rotational symmetry that you have in an equilateral triangle or a square, or even a linear configuration, what you're guaranteed in a situation like this, and it might not match your instincts, is that the way they'll move is not roughly, but exactly outward in the radial direction from their common center. So if you release those, that's what they do. They go straight out from the symmetry point of the thing. And so if you recognize that, and you can work out the math and show that that's the case with vectors if you wanted to, the only way to balance that is to have something in this common center that's no, let me hold everybody together, pull inward. And of course that's the idea of putting some different charge, obviously opposite in sign, so that while these guys are all repelling each other and this one's going to attract all of them inward just hard enough along exactly the line that they were trying to leave, and pulls it exactly inward, and that's going to balance if you get the ratio of big Q to little q just right. And if that is a solution, or the solution really, for n equals 4, what do you suppose a geometry, what geometry could work for n equals 5 then, with the same thoughts in mind? Yeah, same story, except something like this. Because on their own, without this guy, again, common center, no question, but all of them would want to do this outward from the center. And all you have to do is put something in the center to prevent it, right? But it turns out once we get to 5, something different happens here. There's another configuration that's possible. There's 2 of them that work. And any idea what that might be? Much more painful to work out by hand. Yeah? Yeah, the triangular, what do they call that? The tetrahedron? So with something right in the center, and that would just be like, oh, my brain hurts, and if you want an exercise in vectors, have at it. But the easy one to work out is this. Here's one problem that you run into, though, is every configuration we're talking about, starting even with this guy, equilibrium, yes, but there's 2 different kinds of equilibrium, stable and unstable equilibrium. Stable equilibrium is like a pendulum that's hanging. You're like, oh, it's happy to hang there, and also if I nudge it a little bit, it comes back to that hanging position. This is the opposite. If you exactly balance something the other way, it's like, yeah, sure, no torque causing it to fall, but if I give it a little nudge, it's like all over. And it's, so it's an unstable situation. In the same way that you could have a ball balanced at the bottom of a bowl, and if you're skilled, at the top of a bowl. One of those is stable, the other one isn't. Minor perturbations to this system cause it to return to the center. Minor perturbations to this, it's like a house of cards, right? All goes crumbling down. Every configuration we're talking about here is unstable. It isn't possible in electrostatics to have charge configurations that are actually stable, which is weird. Why is it weird? Like to say that you cannot take, let's say, an integer number of charges regardless of signs and regardless of configuration and actually make a stable thing of them. Why is that weird?
Because the math we're doing kind of makes it look like they're stable.
Well, that makes it look like they're in equilibrium. We can test the stability, but it would take a little bit of extra work, calculus, some derivatives. But what other subjects do you study that suggest that there's all kinds of things like that all over nature? Does that help? What does that mean in context? Okay. And what does that resemble when you look at the chemistry? Do you guys have to take chemistry? You do, right?
If we have stable compounds of molecules that balance each other out, then it would...
Yeah, if you get a picture of CO2 in a chemistry book, it looks exactly like this. Like, oh, it's a linear molecule. And that's what it, I mean, it might not draw lines, and they're like, well, there's a carbon atom holding these two oxygen, and that forces you to go like, wait a minute. 3 charges holding themselves together in an obviously stable molecular format, and yet the physics tells you it's not possible. Or I just told you and it's a lie, but it's true. you can't make that guy actually stable. And so that certainly begs a question. What's going on here? So I think I told you the story is that this isn't a molecule of carbon dioxide. It's a horrible picture of carbon dioxide. The atoms themselves are not particles, like point particles like we're treating them. They're actually waves. And even in a stable molecule that looks like a static structure, it's not. It's dynamic, but it's a dynamic standing wave. So it's moving, but you can't treat the mathematics of it to find a stable thing unless you do wave studies. And so you do quantum mechanics, and everything's a wave equation. And then you can find stable things, but they're not really stationary, and they're certainly not point particles. That's just a fact. And it had to be a fact that was already getting people in the first part of the 20th century to go like, wait a minute, electrostatics says that molecules can't exist in nature, but they seem to. So what's going on here? And it's a huge clue. You can't actually do things like we're doing and assume that molecules have this sort of structure and get anything to be stable. And so it's a fun exercise, but this isn't a molecule and isn't a good representation of one. And yet in some weird, depending on how you're looking at molecules, sometimes point particles held together by forces can make sense, but not quite like this, and certainly not by Coulomb interactions. So it's a fun thing. How would we do the math to work out the ratio of big Q to little q in a problem like this? Of course, you could brute force it with this. Probably the only annoying part of doing that is to figure out, all the side lengths, the distances. Once you have this, what does that work out to be? A over root 3? And then you'd have to figure out, I guess, to get these coordinates, where these guys are, and the A over 2 for the x is fine, and I don't know what this would work out to be, something uglier like 3 minus root 3 over 3 or something, I don't know. So, but that would hurt a little bit. It's possible, you could do it. But symmetry might be your friend for a problem like this, in the sense of, first of all, do I have to worry about this guy? No. You might look at it and be like, I think I do. And I think maybe what you maybe should just catalog, you could prove it to yourself once and then just forever have it cataloged. If you have something, nobody maybe would question the 4-point symmetry. If you put like big Q here and little q, little q, little q, and little q, it's easy, I think, to convince yourself that this guy is stable with this 4-fold symmetry, because you look at this and you're like, okay, it's going to be pulling on the corner, so this corner, remember, it's going to be opposite charges. So say these are all positives around the edges, this is negative. So this guy gets pulled this way toward that corner, and immediately you can look and be like, oh, but there's one over here that's exactly canceling that vector going this way. So it doesn't get pulled along that axis, and then you make the same argument the other way, and you're happy to conclude that, oh, I don't have to worry about the one in the center. But what's different with odd symmetries is that you look at this and you're like, I don't know. It's pulled this way and it's pulled this way, and none of those vectors cancel each other as as pairs, and so you might think maybe it is, maybe it isn't. What if it was 5-fold or 7-fold or 9-fold symmetry? The way the math works is it's always, if it has equal divisions angular-wise. So it's, if it wasn't an equilateral triangle, it doesn't work. But if it's threefold or fivefold, if it's looks like a pentagon surrounding the center, it's always stable, even if it isn't in this paired-wise force stable format. So you don't have to worry about that. You can prove it to yourself later if you want to make sure that I'm not telling you fibs. But we don't have to worry about the inside. And so then you just look at the corners and you're like, well, which one do I want to treat? How do I want to think about the directions? The whole goal is if I can, let's say, take this guy and find that it has no net force, then I'm good. All right, so how do you want to go about doing that? First of all, which form between generic, I guess I erased it, between the completely generic magnitude version of Coulomb's law and kind of having to manually think about directions. Would you want to use this or would you want to use this? What's the preference if you can make it work? Yeah, I do the magnitude one, and again, there are cases where that would absolutely not be my answer. Even the first problem wasn't so painful to do this way. And if it's easy to write down the coordinates, it's really not bad. But this one, like I said, you're going to spend 5 minutes or so working out the geometry to make sure that if you considered, let's say this is the origin, like what is this guy's coordinate? X coordinate's easy, it's half the A. The Y coordinate, you're going to have to sit there and think about it. And of course, maybe you could just make a 30, 60, 90. You could do it that way, and maybe you should as an exercise. But symmetry, because it comes up in a lot of places and it's useful to think along those lines, is maybe just a good idea this once to think, well, okay, this guy sitting on the top, if I satisfy that, I satisfy all the corners, because obviously I could just turn it 120 degrees and it's the same picture again. So if one corner is satisfied, all corners are satisfied. And so how would I write it out to know? I mean, how many forces acting on this guy? Three. All right, so maybe I'll draw a new picture right here, a little cleaner picture. So we have this triangle. We have the one at the top, and let's label them. 1, I guess I didn't, did I already? No. 2, 3, 4. So if I wanted to write force on 1 due to 2, or draw it in the picture, what's it going to look like? In which direction is it going to point? On this guy that I care about due to that guy. Yeah, it's going to be repelled because they have the same magnitude, so I'll just draw it as a little dotted line. So this is F1, 2 vector. What about F1, 3? Yep. Like perfect mirror image if I consider the vertical as my mirror. And F1, 4. Yeah, and that's because they have opposite sign. If it wasn't opposite sign and that was going up, there's no hope, right? So that's F1, 4. Oops, 1, 4. So if you look at that, how could I use symmetry to make my life easy? Like what could I avoid calculating altogether? Yeah, I don't have to worry about the x components. And just realize, you're like, oh yeah, that's obvious. Well, it wouldn't have been obvious if I decided to focus on this guy, because then the forces are going this way and that way. X doesn't cancel, and neither does the y. So our job is easier done if we're like, oh, you know what? I'll just consider, the usual x and y coordinates, and I can do away with the x's because as much as this vector is pushing rightward, this one's going leftward. So I don't even have to worry about that. All I really care about is, do these two upward components match the singular downward one that you get from the middle? And so I could do that. If you imagine the two upward components, we got, which is, imagine how much upward components the F12 and the F13 have. It's going to be the same, meaning that upward component matches this one. So you can just find one of them and then double it. And so whatever that is has to be equal to this guy. So the one downward pull toward the center has to match the sum of the two upward components there in the corner. See if you can get that math done in 31 seconds. Maybe not. That was well timed. I didn't do that. I must know. Didn't even give you 31 seconds. Maybe work that out, and we will start up in the next class on that discussion. If you see where this trend was going, 5, 6, ... gets to big values. And so the next place we're going to go with our discussions is, what if it goes to big? Meaning kind of pretending like limit goes to infinity, which represents continuous charge distributions in nature, and so that's the next discussion.